what I plan to do is go through the concepts as fast as possible, and I will focus on the doubts asked by students. If they don't understand any concept, we are going to focus on that. So fluorescence spectroscopy. Fluorescence spectroscopy is a type of molecular luminescence spectroscopy. Luminescence is a phenomena where the light is emitted by the substance. It's called as luminescence. Lumen means light. Okay. There are three types of luminescence methods for spectroscopy that are available for analysis that are available: molecular fluorescence, phosphorescence, and chemiluminescence. Let us see every type of fluorescence one by one. Fluorescence or luminescence, I should say. In each of these three types, molecules of the analyte are excited to give a species whose emission spectrum provides information of qualitative or quantitative analysis. So basically, analyte is emitting characteristic electromagnetic radiation. If we can measure it, we can get information what is present in the analyte and how much it is present in the analyte. So methods known collectively as molecular luminescence. So there are three types of luminescence. Fluorescence. It involves absorption of photon followed by short-lived excited state. Generally, it is singlet state, and then emission of photon. Absorption of photon and emission of photon. The photons have different wavelengths in fluorescence spectroscopy. In phosphorescence, absorption of photon is followed by long-lived excited state, triplet state, that interstate crossing, that singlet is converted to triplet. So triplet state is, you can say, comparatively long-lived, and then it is followed by emission of photon, which brings the molecule to the ground state. Third is chemiluminescence. As the name itself is indicating, there is some chemical reaction involved. There is no excitation source. Okay. Specifically, though, there is no electromagnetic radiation which is acting as excitation source. Chemical reaction provides the energy to excite molecule, which is followed by emission of photon. Luminescence, it is associated with high selectivity. When we say selectivity, it means out of many molecules, only few of them will be associated with the luminescence. It is also associated with high sensitivity. That means small energy gain or loss by the analyte molecule will be associated with significant change in luminescence. So these two, selectivity and sensitivity, as a combination provides strong signal against dark background. Now, it is used as a detector for HPLC as well as capillary electrophoresis. Now, coming to the theory of fluorescence and phosphorescence, although phosphorescence is not in their syllabus, but their theory is overlapping. So, we will see both the phenomena. Moreover, theory of phosphorescence is in a way complementary to the fluorescence to understand the complete excitation and relaxation of any molecule by electromagnetic radiation and relaxation by radiant pathway. Okay, types of fluorescence. There are two types of fluorescence. When we are talking just about fluorescence, they will be of two types. One will be called as resonance, where emitted lambda and excited lambda, they are same, they are equal. Now, there is another which is called as Stokes shift, where emitted wavelength is longer than excitation wavelength. So this is associated with high energy, and this is associated with lower energy. That means high energy is absorbed by the molecule, and while it is emitting wavelength of longer. It is emitting light of longer wavelength. You remember this phenomena, resonance fluorescence. We are going to study this again in one of the next chapters. Example of Stokes shift is molecular fluorescence. Now, let us consider what is singlet state and triplet state. It depends on electron spin and excited states. When in a molecule, electrons are excited paired, it is called as excited singlet state. It leads to fluorescence. When in a molecule, electrons are excited and are unpaired, they are called as excited triplet state and they are responsible for phosphorescence. See, at a ground state, in a molecular orbital, the electrons have anti-parallel spins. That means they cancel out spin of each other. Okay. It may happen that one of the electron is gaining the energy by absorbing the photon and jumping into higher energy level. So the spin of the electron still remains anti opposite to each other, but because one electron is excited, this state is called as excited singlet state. Please note that electrons are present anti-parallel to each other. It may happen that the electron, by losing some of the energy, is changing its spin. Now, both the electrons are now parallel to each other, and this state is called as excited triplet state. Deactivation process. Once the electrons are excited, going into excited singlet or excited triplet state, what will be the deactivation of those electrons? How the molecule will come back to ground state? Process by which an excited molecule returns to the ground state is called as deactivation. Minimizing lifetime of electronic state is preferred. The meaning, the deactivation process with faster rate constant will predominate. Suppose there are 10 ways to reach from point 1 to point 2. There are 10 ways to go there. So the path, the way which is the fastest one will be adopted for traveling from one point to second point. So same is happening for deactivation. The deactivation process which is fastest will be preferred by the molecule. So as a result, the excited state of that molecule will have shorter lifetime. So that is the second point. Now, radiationless deactivation. This is the deactivation, losing the energy by not emitting photon without radiation. It is called a Jablonski diagram. Jablonski diagram, what does it show? It shows how a molecule gets excited, how it comes back to ground state by releasing the energy in the form of vibrations or in the form of radiation. These four levels which you can see over here, they represent, all of them represent ground state. All of them represent ground state. Although it is a ground state, it is associated with four vibrational levels. It is associated with four vibrational levels. Now let us not go into deep into vibration levels. We are not interested as of now into vibrational levels. On left hand side, if you will see, there are continuous gray color arrows which indicate that from all the levels of ground state, molecule may go into excited state. If the energy is very high of the absorption, molecules will enter into S2. If the energy is comparatively less, they may enter into S1. S1 has lower energy, comparatively lower energy than S2. It may happen that a molecule may land at any random vibrational state, not necessarily which one. Okay. Now, it may internally come down to the lower vibration state by releasing the energy in a vibrational relaxation. We are going to see what is vibrational relaxation. Okay, it may come down to lower and lower energy levels. There will be some region where vibrational levels, or I should say the lower vibrational levels of S2 overlap with higher vibrational levels of S1. You can see that these three have almost same energy as these three. If that is the case, such thing happens, then the electron may change, may get itself transferred from S2 to S1. It is called as internal conversion. It is called as internal conversion. Why internal conversion? Because the singlet state are still maintained. Okay, the electron is still in singlet state. Now, again, the molecule or the electrons of the molecule may come in S1 from S2, or they may come in S1 by directly absorbing the energy from ground state to S1. Okay, anyway, when molecule comes to S1 at any vibrational level, ultimately all the molecules are going to get at the lowest energy level of S1. From the lowest vibrational energy level of S1, there are two possibilities. One, they will emit the photon, give the fluorescence, and jump to one of the vibrational levels of ground state is 0. The other possibility is by internal and external convergence. When we say internal conversion and external conversion, there are some concepts associated with it. But just understand that either by collision or by passing on the motion to the adjacent molecule, the molecule is coming back to the ground state by releasing the energy, which is a non-radiative way of relaxation. So this will not give you fluorescence because it is non-radiational waves, but when it emits photon, it will give you fluorescence. I hope it is clear with everyone. There is still some region of first singlet state. These vibrational energy levels of S1, they overlap, they have almost equal energy of the triplet state. Now, it may happen that some of the electrons which are there in the singlet in these vibrational levels, they may jump to triplet state via inter-system crossing. Why it is called as inter-system crossing? The reason is the system is being changed from singlet to triplet. Please note that a molecule cannot directly jump into triplet state by absorbing the energy. The reason being the electron, one of the electron has anti-parallel motion, and by just absorbing the photon, changing the spin is not possible. So this is inter-system crossing. The remaining processes are same. The only difference is when from triplet state, excited triplet state, photon is released, it is called as phosphorescence. Now, this triplet state has longer, you can say longer stability as compared to S1. Moreover, the inter-system crossing, flipping of the electrons also take time. So all that contributes for delayed luminescence. Luminescence is called as phosphorescence. Let us understand the terms that are involved in this. Internal conversion, vibrational relaxation, intersystem crossing, external conversion, absorption, fluorescence, and phosphorescence. The first term is absorption. The effect of process of absorption is excitation of the molecule. Molecules and electrons within them get excited. Now, what is this process actually? Analyte molecules, they absorb photon. This is very fast process. The process takes approximately 10 raised to minus 14 to 10 raised to minus 15 seconds. As a result, electron is promoted to higher energy state and slightly different wavelength excitation into different vibrational energy levels will occur, because if you change the wavelength, energy associated with will change. If the energy associated with the photon will change, the vibrational energy level will change. What we are talking is, see, suppose this is the wavelength lambda 2. When it is absorbed, molecule is entering into this vibrational level. If you change wavelength slightly, here or here, okay, it will correspondingly change the vibrational energy into which, energy state into which it is getting to convert, getting to transferred. I hope you understood this first term, absorption. Next term is vibrational relaxation. When we say vibrational relaxation, we are looking into these processes. We are looking into these processes. Small blue colored arrow. These are small blue colored arrow we are looking at. Okay. So what is effect? Effect is deactivation, and it is a radiationless process. What occurs in the process? Collision of excited state analyte molecules with other molecules. So it is like one cricket ball is stationary, the other cricket ball is traveling at great speed and it is hitting the stationary ball. When it hits the stationary ball, the ball which was already traveling with high speed, it becomes stationary, and the ball which was previously stationary starts traveling with high speed. Okay, so loss of excess of vibrational energy and relaxation to lower vibrational state. Now, so when, if this has to occur, collision is important. Collision is important. Now, although this is transfer of energy, there is hardly any change in the electronic state. So singlet will remain singlet, triplet will remain triplet, ground state will remain ground state. Now, next term, internal conversion. We talk about internal conversion, we are talking about this process. See, why it is internal? Because it is still single excited state. Although it is the first singlet excited state, it is the second singlet excited state, but as a whole it is singlet excited state only. So singlet is not getting converted to triplet. That's why it is internal conversion. What is the effect of these processes? Deactivation, and the process is radiationless. Now, in this process, molecule passes to a lower energy state. That is, from S2, it will come to S1. But vibrational energy levels of the two electronic state must overlap, and molecules passes from one to the other. When we say the energy levels are overlapping, we are telling that their energies are approximately equal. They will not be exactly equal, it will be very difficult that to occur, but they may be very similar in the energy. When such thing happens, only then this internal conversion is possible. Okay, next concept is fluorescence. It is also a process of deactivation, but when this process occurs, there is emission of H nu electromagnetic radiation. Emission of a photon via singlet to singlet transition. It is short-lived, excited state, 10 raised to minus 7 to 10 raised to minus 9 seconds. Next, inter-system crossing. This process is deactivation process and it is a radiationless process. Now what happens is in process is spin of electron is reversed, leading to change from singlet to triplet state. This occurs more readily if vibrational levels of two states overlap. We have seen this in the diagram. It is common in molecules with heavy atoms like iodine or bromine. Next is external conversion. Now let us see where external conversion is occurring. The internal system crossing हमने अभी देखा है यहाँ पे. Now external conversion is happening over here from S1 to ground state and from T1 to ground state. Let us see what is that, how it is happening. It is again a deactivation process and it is a radiationless process. Collision of excited state analyte molecules with other molecules. Now, molecule relaxes to ground state without emission of photon. So, what is difference between? Can anybody tell me external conversion and internal conversion? What is difference between them?
सर संकेत है सर, एक्सटर्नल में ग्राउंड स्टेट में मॉलिक्यूल जाएगा और इंटरनल में ग्राउंड स्टेट में नहीं जाएगा सर.
वेरी गुड संकेत, बट देयर इज मोर टू इट. सी, सिर्फ ग्राउंड स्टेट में नहीं जाएगा ऐसे नहीं है. व्हेन इट इज इंटरनल कन्वर्जन, S2 का मॉलिक्यूल S2 में ही रहेगा, S1 का मॉलिक्यूल S1 में ही रहेगा, T1 का मॉलिक्यूल T1 में ही रहेगा, S0 का मॉलिक्यूल S0 में ही रहेगा. When it is external conversion can occur only when the molecules are at the lowest energy level of S1 or lowest energy level of T1. Additionally, when this external conversion occurs, the molecules will get transferred from S1 to ground state, T1 to ground state. External conversion cannot occur from S2 to ground state.
Yes, sir.
Okay. Next concept is phosphorescence. It is a deactivation process. It is associated with emission of electromagnetic radiation. Now, emission of photon via triplet to singlet transition. It has to be triplet to singlet. Now it is long-lived excited state. It takes 10 raised to minus 4 to almost 10 seconds. If those concepts are clear, there is one more additional concept. It is called as quantum yield. Now, quantum yield, theoretically, it is very easy to understand. Suppose you have 100 molecules. You have 100 molecules. Out of those 100 molecules, suppose 50 molecules are getting excited. You have total 100 molecules. Out of 100 molecules, 50 are getting excited. And out of those 50, 25 are giving you luminescence. So quantum yield will be 25 molecules which are giving luminescence divided by 50 molecules which got excited. This ratio will be called as quantum yield. Let us see the description of it. The quantum yield or quantum efficiency, which is also called for fluorescence or phosphorescence, is the ratio of number of molecules that are luminescence to the total number of excited molecules. Please note that there is no consideration of how many molecules are present overall. It may happen that there will be 1,000 molecules out of which 50 getting excited. There may be 100 molecules out of which 50 getting excited. There may be 60 molecules out of which 50 getting excited. So out of, if it happens that for say 1,000, it gives measure of how efficient the fluorophore within the molecule is. Now, any guesses what will be the fluorophore? The similar word was chromophore. So what will be the fluorophore?
Molecule that gives fluorescence.
Acha, my question to you, if compound has fluorophore within it, can we call the entire compound fluorophore or some part of the compound as fluorophore? Functional group or part of the compound which is responsible for fluorescence will be called as fluorophore. Like in a molecule, the part of the molecule which is responsible for absorption is called as chromophore. So the part of the molecule, see, entire molecule cannot be fluorophore. Impossible. So there will be always some part of the molecule which is responsible for fluorescence. Okay, anyway. So a quantum yield is equal to, means that every excited molecules deactivates by emitting photon minus such a molecule is considered a very good, oh, I said minus, I'm very sorry. Such a molecule is considered a very good fluorophore. Now, this is the formula for it. Total number of luminescing molecule divided by total number of excited molecules. This is the formula for it. See, there are different processes occurring within the molecule. Okay, there is fluorescence, there intersystem crossing, there are external convergence, there are internal convergence, there are dissociation, and it is photo dissociation. PD is photo dissociation and D is simply dissociation. Sometimes dissociation is also we can say considered as deactivation. There is photo deactivation and there is simply deactivation. Okay, so how fluorescence and structures they are related. Someone rightly said that it is associated with pi bonds. So low energy pi electrons are promoted to high energy anti-bonding pi electrons. We are talking here about molecular orbitals. Now this is generally observed in aromatic compounds. If it is the case, then you will observe most intense fluorescence. Now, heterocycles, when we say heterocycles, we need to consider n electron also. Heterocycles do not fluoresce. Heterocycles fused to other ring, they do fluoresce. Heteroatom increases intersystem crossing, therefore constant of or the yield of fluorescence decreases. So whenever there is heteroatom present in the zinc, instead of getting fluorescence, you will get phosphorescence because n electrons will promote it. It will provide the stability that is required to cross from excited singlet to triplet state. Conjugated double bond structures exhibit fluorescence. Structural rigidity, that means the molecular structure which are difficult to rotate or bend. Okay, they are rigid structure, sterically hindered structure like naphthalene, fluorine, or biphenyl. Flexibility increases when quantum yield of fluorescence decreases. Temperature increase fluorescence intensity with decrease temperature. This is observed because there is If the temperature is decreased, movement of molecules will decrease, so collision will decrease. So deactivation due to collision, it will also decrease. So this is how the fluorescence is related to structure of the molecule. Now observe these all of the ring, and I will ask you. You will tell me whether fluorescence or phosphorescence will be observed. Pyridine. What do you think in pyridine? What will be observed? There is heteroatom there.
Oh no, sir.
You'll observe phosphorescence because there is heteroatom present. What about furan? She's asking phosphorescence. Yes. Okay. Next question to Mr. Shubham Munde. Shubham, what about quinoline? What do you guess? There is heteroatom present, but the ring is fused. Okay, because the fused ring system along with heteroatom, fluorescence is observed. What about fluorine? If you have a rigid ring system which is aromatic, what do you guess? Yes, fluorescence. Very good. Fluorescence will be observed. Same goes. No, I will not say same goes. I will ask you. What about biphenyl? Fluorescence, phosphorescence, or nothing? Okay, fluorescence is the possibility because heteroatom is not present, although there is no structural rigidity to it. Okay, there are uh, few more factors that may affect the fluorescence. Increased fluorescence with increased viscosity, decreased likelihood of external conversion, that is radiationless deactivation. When you can say the viscosity of the solvent is increased, the movement of molecules because of high viscosity is difficult. So collision will be difficult. So external convergence, which is radiationless but due to collision, will be difficult. So fluorescence will increase. Now, heavy atoms such as iodine, bromine increases intersystem crossing as a consequence of quantum yield decrease for fluorescence. Now, when molecules are big and they are forming molecular orbital, the molecular orbitals are fairly complex and there are many molecular orbitals. There will be the outermost orbitals and there will be immediate internal orbitals. Those all orbitals are very closely spaced because the atoms are large involved. So because they are closely spaced, there is okay. So large atoms when involved in formation of molecular bonds, the vibrational energy levels of those molecular orbitals are very close. So intersystem crossing, giving you triplet state, is promoted. So as a result, fluorescence decreases. pH. Now I hope you must have guessed what happens with pH. See, increased resonance structures, it is protonation or deprotonation. If we are increasing the resonance structures, what we are doing actually is we are going to stabilize the molecule. So stable excited state will result in greater quantum yield. Now, it is not always that you increase the pH or decrease the pH, you will always get quantum yield. Sometimes it happens that if you increase the protonation, the protons will attack the electrons themselves. In that case, the stability will be decreased. Okay, pH also influence the emission wavelength. That is changes in acid dissociation constant with excitation. See, this is if you change the structure of molecule by any means, here it is pH, the characteristic wavelength will get changed. Some example is given here. Okay, this point we will cover next lecture, fluorescence intensity and concentration of the analyte.